Welcome to EDU World Space.
When spectroscopy was first getting done on the hydrogen atom, people really didn't understand the mathematical basis for this, but they did discover several series in the spectra of hydrogen, the spectrum of hydrogen. And depending on who studied the series was given the name of a researcher. So the most famous is the Balmer series. And in the Balmer series, the bottom state of the electron is n equals 2. And we now know that what's happening is the electron is falling from some greater n to n equals 2 to make an emission. Lyman is a similar thing, but the transition winds up in the n equals 1 from anything higher up. And likewise, the Paschen series is anything higher going to n equals 3. And what we'd like to do is find the shortest wavelength in each series. So a reminder that the shortest wavelength goes with the most energy difference between initial and final states. So where do these all start if you have the greatest energy difference? What the initial state turns out to be is what's called the vacuum limit, with the idea that the electron becomes free from the binding of the proton with n going to infinity. And in that case, the photon energy that gets released in the transition is a very simple expression. It's basically equal to absolute value of minus 13.6 electron volts. We'll drop the negative, divided by n final squared. So we're simply going to have to square the n final in each of these cases to figure out the shortest wavelength in each series. So let's go ahead and do that. The energy of the photon, by the way, is good old hc over lambda. And we will use atomic units, 1240 eV nanometer over lambda. So for the Lyman series, the shortest lambda, we'll call that vacuum lambda for Lyman. Vacuum Lyman is simply 1240 over 13.6 nanometers, and that is 91 nanometers. Whoops, why am I writing a W for nanometers? Here we go. And that's an ultraviolet, pretty far beyond what we can see, but not super beyond, but we'll just call it ultraviolet. Balmer, lambda vacuum Balmer is 1240 times 4 over 13.6. So there's your n final squared coming in as a 4. And this turns out to be 365 nanometers. And we'll call that near ultraviolet. It's just a little bit beyond what most people's eyes can perceive. Paschen. Let me spell Paschen correctly. So that would be 1240 over 13.6. N final is 9, n final squared. and that is 820 nanometers, which is relatively near infrared. So we can see why maybe these series were named after the researcher who studied the spectrum, simply because you would need different tools to study the ultraviolet and infrared regions that we cannot see with our naked eye, compared to even the near UV, which may be easier to detect than anything else in the Lyman series. So yes, they needed different tools to study each of the series. Lyman needed ultraviolet tools. Balmer, most of those are in the visible spectrum. And Paschen, most of those are in the infrared.